Thanks so much for the invitation. And so today I want to talk about deep learning in two parts. And so the first part, which will be at least mostly before lunch, I want to talk about the machine learning side of things, about how we use these tools essentially to process unstructured data, by which I mean things like text, images, audio. And then after lunch, I want to talk about the econometrics side of things, right? So now you've used some of these tools to take unstructured data, to take text, images, to incorporate it into your research, but you want to get the econometrics, right? You want to account for the fact that you've done this, that this data, that these predictions that you've used deep learning to predict, they're not the truth in some deep sense. They're probably measured with error. How do you account for that? How do you get the econometrics, right? And so we're going to have kind of these two separate parts. You know, if this goes over a bit, that's fine. We don't have to spend the entire hour and a half on econometrics. And I'm going to have a really heavy emphasis on examples. And so these might not be examples that everybody is kind of personally interested in, but hopefully they give you a flavor for how these tools are used. I'm not going to go into technical details. You know, that could take an entire course. But I have a website, and you'll see the link in these slides that point to lots and lots of technical resources that have lectures there. And so for people who are interested but kind of want more information on the technical side of things, I'll point you in the right direction. All right, so with that said, we'll go ahead and get started. I don't know if you have like a procedure on questions. Do people want to jump in, if anything, or? Whatever you prefer. Okay, yep, if anything is unclear, jump in. We'll also try to leave some time at the end just to have like a broader discussion, but if I've lost people, please do let me know. All right, deep learning has revolutionized the processing of unstructured data. And I said unstructured data are data that, you know, are too high dimensional, too complex, too uninterpretable to plug directly into your analysis. And so what you want to do is to use deep learning to extract information that you can then understand and analyze directly. You know, in economics, we might think about extracting sentiment or topics from text. You know, in other fields, they might be extracting information that they can use for a self-driving car or to diagnose disease. And so deep learning has transformed kind of all these disciplines by making it much more feasible to accurately and on a large scale extract information from unstructured data that can then be used to perform whatever analysis that you happen to be interested in. And so within economics specifically, we have massive quantities of data in their raw form that you can't really compute with that could transform our analyses if they're processed into a format that can then be used for computations. So text is probably the prime example, huge amounts of information there. Data can also be tracked in images, you know, whether that be images of documents from archives, satellite imagery, aerial photographs, social media images. There's also audio and video, which is essentially a bunch of images in rapid succession that's combined with audio. And so while this raw information is very different, the methods that we use to convert images or text or audio into computable information are quite similar. And they typically will draw on the same neural network architecture, which is called the transformer. So you can use a text transformer for text, and kind of all the large language models that you've probably heard of are transformers. You can use an image transformer for images. Actually, interestingly enough, the state-of-the-art model for audio was pre-trained first on a large number of images. And so the architecture is just kind of very similar. Then they use the image of the audio spectrogram, of the waveform created by sound to analyze the data. And so you can have very different types of data, but the toolkit is essentially very similar. Our goal in processing unstructured data is to take this complex, diverse information and learn a mapping into a format that is easier for us to process and to understand. And so if you want to say that kind of in a technical way, we're going to take our high dimensional text, you know, think of raw text as a bunch of sparse vectors. The dimensionality of the vector is the size of the vocabulary. So if it's English text, it might be the size of the English language that's all zeros except a single one, which is the word that is used. That is a very difficult object to compute with. Think of an image as RBC pixel data. Again, very complicated object to compute. We're going to take those complicated objects and map them into a continuous vector space. And what I mean by that is you're going to say take a patch from your image or a word out of your text, and you're going to map that into a vector that's much lower dimensional, like 512 would be a typical dimensionality, and it's going to have numbers in every position of the vector. And we know how to work with those low dimensional vectors really well. So at its core, deep learning is an approach for learning these representations, these continuous vector representations of data from empirical examples. And so in deep learning, you don't tell the computer the rules that you're going to use to map that high dimensional data into something more low dimensional. It learns how to do that from empirical examples that are fed to the model. And so you might be wondering at this point, why are we going down this route at all? Why use a neural network to transform the raw data versus just trying to work with them directly, or you kind of using existing methods like, say, a keyword search in the text? And so there's essentially three reasons why neural networks are so powerful and so transformative when it comes to working with unstructured data. And so the first reason is transfer learning. Deep neural networks incorporate relevant information in their parameters from exposure to massive scale data. And so, state-of-the-art language models nowadays, they've seen trillions of tokens of text in their pre-training. I think it's hard for us to comprehend just how much text that they have seen. Okay, whereas if you devise your kind of own method, it's just relying on whatever information you bring to the problem. With deep neural networks, you can leverage, a model that took millions of dollars to train on trillions of tokens of text, and it basically already understands language, and now it just needs to understand your problem, like as a subset of that.
For instance, one can sort of think about information loss. So we're kind of reducing dimension, and in a way we may just be kind of getting rid of a lot of irrelevant detail and encoding the information we want to work with. But in some sense, there's also potentially information loss, right? Or there's a notion, is there a sense in which one can sort of think about that dimension reduction and whether we're extracting something informative or whether we're losing something relevant?
Yeah, so I think that if you want to think about neural networks in a broad sense and what they do, I think kind of one powerful way to think about them is they're just a technology for compression. And so let's say you can take the entire internet, which is just an unfathomable amount of information, it's trillions of tokens, you train this model, and essentially what you've done is to compress it, like let's say in the case of GPT-4, it's like 176 billion parameters, right? And so you've taken trillions of things and you've compressed it down to billions, which is a huge reduction, right, in the size of the information. And I think that's one way to think about it. And of course, there is loss. These models cannot perfectly reproduce every text that they've ever seen. And I think the question becomes, is that loss kind of relevant for your problem? And it may be that you need to tune the model on your own data rather than using it off the shelf, and so that its parameters learn to attend to the most relevant information for your problem. All right. So the second reason, I know this is basic for some people, but I do want to kind of go over this because I don't want to assume everybody has a lot of background. And so the second reason why deep neural networks are so powerful is they take into account context. And so if you were just to take raw pixels from an image or words from a text and map them to vectors without thinking about the context that they are in, that's gonna, that's not gonna be a very effective way to do things, because the meaning of a word, the meaning of a pixel depends on the context. Words can change meaning drastically if you put them into different contexts. And the transformer architecture really excels at being able to map the context in which a word or in which a pixel appears into the representation, the vector representation of that word or pixel. And then finally, deep learning makes problems incredibly scalable. And so it's really unwieldy to work with raw text or image data, whereas there's extremely optimized tools for continuous vector computations. So for example, in some work that I did, we were able to make 10 to the 14th exact vector similarity calculations on a single kind of mid-range, by now quite old GPU card in a few hours. There's a library called Facebook AI Similarity Search. It was made by what at the time was FAIR, what's now Meta AI, and they just made it public, and it makes vector similarity computations at kind of incredible speed. And so when you can get your data into this continuous vector format, it's incredibly quick with modern GPUs. To make a very, very large number of calculations in a very small amount of time, and so you can do problems at an unprecedented scale. All right, so this is just an illustration of what I mean by context. And at the top of the image, you see kind of a figure representation of how bag of words works. And so bag of words, which was used traditionally in NLP, essentially for each word, you separately map that to a vector, then you have some feed-forward neural network layer that maps that into probabilities. Say, is the sentiment of this text positive, negative, or neutral? And each representation for each word depends on just that word. Whereas with a neural network, what we're going to do is take these raw texts and feed them into some complicated function that then takes into account the context in which each term appears. And I think if you learn sort of one thing about neural networks, it's that deep neural networks are the state-of-the-art tool for estimating really complicated functions. And that's essentially kind of all a neural network is a really complicated function that you're going to estimate by learning from empirical examples. So computation has a long history in economics, but I think it's fair to say that in the 1990s, the advent of personal computing really revolutionized the discipline. Economics used to be primarily theoretical, it became much more empirical. It's hard to imagine development economics existing without kind of personal computing, which makes it possible to easily collect your own data. And I think today kind of we're, in the midst of a similarly transformative time where advances in GPU compute and the availability of very cheap cloud compute, again, have the potential to transform the types of data and questions that we can study. So for a relatively small amount of money, I can spin up 1,000 cheap CPUs on Azure, run them all day long, and it's going to cost me, not maybe $100, maybe even less, depending on the type of CPU. I obviously could have never had 1,000 CPUs in my office. And so once I have a neural network trained, I can just process data at an incredible scale that would have been unimaginable, say, 15 years ago.
Melissa, do you think there can be any trade-off there? Because you could argue that in some sense we could also lose something, right, in terms of the ability of theory to impose structure as to what are the relevant dimensions of the data and test mechanisms. Do you think there's any kind of potential trade-off?
I'm definitely not saying that we should abandon theory. I don't know, maybe people think we're going to go crazy over neural networks and that's what's going to happen. So I'm not making a statement that that we should abandon theory, and clearly every paper that you write will have an opportunity cost that you're not doing some other type of research. And so I'm certainly not advocating that everybody should be using a deep neural network and doing exclusively big data work. I do think that there's sort of this tension, I guess, between the way that we traditionally do things as economists and the way that these tools work. Maybe we'll get into this a little bit more after lunch on the econometrics side of things. You're not going to characterize the convergence rate of, 176 billion parameter deep neural network. But, I'll talk then about, ways we can think about deep neural networks from an econometric standpoint that treat it as a black box, but still fit within kind of our traditional models that we've had kind of for decades to think about things. You might say that there's like a kind of a similar tension with theory, that you might get this neural network that's incredibly predictive, but we have no idea, kind of why that is the case. And so I think that again, is like a tension that has to be navigated. Like, I'm not a theorist, and so I'm not the best person to kind of speak about that, but I do think that there is this tension between like, okay, we fully understand what this thing is doing, but it's really inaccurate because the real world is super complex, versus, okay, we have a very predictive model, but we have no idea why it's predictive. And I think, there is, people are thinking about how to navigate this tension, and I think there's going to be a piece coming out in the JAL about neural networks and theory and kind of trying to navigate that tension. And so people are thinking about this, but it's definitely a huge open question. All right, these are awesome questions. All right, so what I'm going to focus on today is using neural networks to make predictions from unstructured data. So the kind of basic framework that I want you to have in mind, and I'll kind of develop this more formally when we talk about the metrics later, but essentially, let's say you have like 50 million newspaper articles. You can't plug those newspaper articles directly into your regression. You just want to know how many of those newspaper articles talk about economic policy uncertainty. And so essentially what you want is a 0-1 value for each newspaper article. Does this discuss economic policy uncertainty? But you don't have that. The newspaper didn't publish that information when they published the article. And so your goal is to impute that information with a deep neural network. And so kind of that's the type of problems I want to talk about today. There's also lots of other really fascinating uses, like people are using deep neural networks to approximate solutions to NP-hard problems. And I think that's super interesting because while they're not necessarily like better on a given problem than traditional techniques, they scale like way better. And so you could solve like a really complicated routing problem or something. There's, as I said, there's applications in theory. There's tons of applications. I couldn't possibly talk about all of them, and I'm not qualified to talk about all of them like in a short lecture. And so what I'm going to be focusing on is you have a piece of unstructured data, so like typically a text or an image, and you want to measure something in that. Like, how do we do that? And conceptually, I'm going to divide these problems into 3 different groups. And if this doesn't make a lot of sense now, I'm going to give you lots of examples. And so the first type of problem is you want to impute some continuous number. So let's say you have some satellite images and you want to locate in those images where street vendors are located because you're trying to measure economic activity. So essentially you want to impute the coordinates of the street vendor in the image. That's a continuous number. So in machine learning, we call this a regression problem, not to be confused with regression in the way that we typically use it in economics. So when we're in machine learning world, regression means we want to predict a continuous number. On the other hand, we might want to impute a pre-specified discrete class. And so in the newspaper article I gave, we want to know, is this about economic policy uncertainty, yes or no? That could be multi-class. It could be multi-label, which is the what we call a classification problem when a given text or image can fall into multiple groups. So this is about both the labor force and domestic issues, and that's in the same newspaper article. Okay, but what's important here is these classes are pre-specified. And then the third type of problem, which we'll see actually comes up a lot, is that we want to impute relationships in data where the classes are not specified ex ante. You're in a world now where you have this big data set, you want to go explore it, but you don't know, you don't know what the classes are ex ante. You don't know what the topics are, et cetera. And so we'll see lots of examples of this type of problem. Okay, so those are kind of 3 different and distinct, and the methods we're going to use for them are going to be distinct. And these are kind of the main 3 types of problems that we have when we're trying to impute something from unstructured data. And so the basic idea is we have this neural network, and it's going to encode this unstructured data into these low dimensional vector representations, right? They're low dimensional, they're dense, they have a number in every position, they take into account the context. That's what the neural network does. Okay, and so the researcher can either use these representations to predict whether the raw data belong to a pre-specified class, and there you just add a classification layer, which is going to map these vectors into class probabilities. Or regression works analogously. If you add a layer to the neural network that combines kind of those vectors that you've predicted to represent your text or image, and it takes those and maps it to a continuous number. And broadly speaking, generative AI performs classification. And so what, say, GPT is doing, is you feed in your prompt at each kind of time step in the text, it's predicting a vector, a dense vector, and then it's mapping that vector to the most likely word in the English vocabulary. And there's some stochasticity in there. You can change that with the parameters, as those of you who played around with it know, but like the basic idea is it's creating kind of vectors at each time step in your text to predict the next word, and then it takes those vectors and it maps it into what's the most likely word in the vocabulary. And so we can think of generative AI as also a type of classifier. But the alternative is that you don't have to add that classification layer to map those vector representations of your text or image to class probabilities or to a continuous number. You can work directly with those vector representations. And these are referred to as embeddings, and we're going to see lots of examples where it's advantageous and makes the problem kind of much easier to work directly with those vectors. All right, so this is like a classification flowchart. So suppose you have, let's just say that you have some text, maybe it's posts from social media, maybe it's news articles, etc., and you want to group those into classes. What tool might you want to use? And I'm going to go into this in a little bit more detail, but this is just an overview. So there's a series of questions to ask yourself. Are the classes known ex ante? If the answer is no, you cannot add a classifier layer to your neural network to do predictions because you don't know what the classes are. A classifier layer maps directly to pre-specified classes. So if you don't know what the classes are, say you don't know what the topics in this data are, you cannot use kind of a traditional classifier. Instead, you have to work directly with the embeddings. On the other hand, if the classes are pre-specified, ask yourself how many classes there are. If there is a lot, like say, 100,000, you're not going to be able to compute the classifier layer and forget doing a classifier. But even if there's less than 100,000, to train a classifier, the model needs to see all those classes in training. And you might not have labels for, 10,000 classes, right? And so if you don't have labels for everything, again, you might want to use embeddings. On the other hand, if you don't have too many classes, you're able to have labels for all the classes. Then I think the next question to ask yourself is, what's the domain? Are you working with 16th century data on the Spanish Empire, or are you working with some data that you've scraped from the web? If you're working with some data that you scraped from the web, you might be able to use generative AI to do the classification, and that web data is going to look kind of like what, say, GPT or Gemini was trained on, and it might work pretty well. On the other hand, if you're working with like the 16th century Spanish data or something pretty niche, you can always try it, but it might have a more difficult time. The other thing to ask is like how fine-grained and technical is the distinction you want to make? And again, if you're trying to make some very fine-grained distinction, again, you might have to kind of train your own classifier model. If it's kind of a general distinction, you might be able to use GPT. And so I'm going to talk about this more and give you some data in a minute. I always say, why not try GPT, try Gemini, try Claude, see how it does. And if it doesn't do well, then you know that it's cheap to try it. But let me now go into classification in more detail. And so again, in traditional classification, we have a neural network, it's mapping our text. So let's say we have text. It's gonna map that text to a series of vectors, kind of one for each term or token in the text. And then we add the classifier layer and it maps those representations for each of the terms into our class probabilities. And so this is how we traditionally do classification. We assign the class to be the one with the highest score. If it's like a multi-label problem, maybe we can assign multiple classes if they're above some threshold. And I'm not going to go into the technical details of this, but I have a JEL article. I think there was like a reading list that had it. And there it talks a little bit more about classification and what the objective function is. And really central to the power of transformer neural networks, which is the architecture that you're almost always going to be using, at least for the time being, is the ability to use the same pre-trained language model as the backbone for a wide variety of classification tasks. And so this figure here is just adapted from the original BERT paper, which was one of the first transformer large language models. And so, you have those blue boxes there. Those are the terms in your text. And you're going to feed those into BERT. And BERT is a transformer neural network. It's going to take those vectors and pass them through the neural network, kind of through multiple layers of the neural network. And kind of at the end of the neural network, you're going to get those orange vectors out, which are dense vector representations for each term in that text that take into account the context in which that term appears. Okay, and so if you want to do classification at the text level, so like, is this newspaper article about economic policy uncertainty? What you do is to just add a classifier layer to that first token, which is called the class token, and that's a token that BERT or whatever large language models, they all have a class token at the beginning, and that class token represents the entire text. You just add your classifier layer there, and it maps to yes or no, and you choose the one with the highest probability. On the other hand, you might want to classify the relationship between two texts. And so, you might want to say, are these two texts duplicates of each other? Are these two texts about the same topic, etc.? And so the way you do this is you jointly embed them. So you feed them into the transformer large language model at the same time, and you put what's called a SEP token, which is a special token that means separator. And the model has seen this in training. It understands what that means. So you put the SEP token between them. And again, then the transformer will do its magic. It's going to get fed through the neural network. And if you want to classify if they're the same or different, again, you just put a classifier layer on that first token, the class token that represents the full text in yes or no.
This is a very obvious question, but when one does that classification, can one also extract and recover the probability distribution? So to get a sense of how certain the neural network is of whether this is A or B. As humans, we have a notion of that, right? Which of the cases are very clearly in one bin versus the other, versus which it's very hard to discriminate. Can one kind of recover the full, discretized distribution of probabilities underlying the classifier?
You could do that, but it wouldn't really be meaningful because what that looks like is going to depend on how you normalize the neural network, right? So at the end of the day, all that's really meaningful is which class comes out as most likely, because that's what it's trained to do. And so, suppose you had, if you had data, say on, certainty, you could train a model to distinguish that specifically, or maybe to predict a continuous number. But you would have to have kind of the training data and explicitly train the model to do that. And so the probabilities from the classifier, they're not really, we call them probabilities, and that's just what the literature calls them, but they're not probabilities in a statistical sense. The model has just been trained kind of to put, the highest weight on the most likely class, or to put, all the classes that are positive above some threshold. And if you change the normalization of the neural network, you're going to change kind of what those class probabilities look like. If the model is well trained, it shouldn't change which class is the most likely, but you really can't, unfortunately can't interpret them as probabilities. The whole literature calls them class probabilities, but it's really misleading. I guess a statistician wouldn't call them probabilities.
But that seems important, right? Or something to be aware of when one's doing the classifying, because it could be that some of these assignments, it's actually very hard to discriminate whether it's yes or no, and we're doing that. But yeah, actually, there's not much information in the raw data, right? That seems sort of important to know.
Yeah, I mean, I think that. Yeah, I mean, I think it's absolutely important to know, and I'm going to spend the entire kind of second half of this arguing that you need to know that, you need to label data, you need to know how well this thing is doing. And you can always look at places, there is like a classification boundary, and so you can absolutely pull out examples that are near the classification boundary, right? And there's an entire literature on what calls active learning, and it thinks about, whether that's helpful to grab things near the classification boundary and label them and add them to your training data. But it's not going to have a statistical interpretation. And if you change how the neural network's normalized, like, how near things are to your classification boundary is going to change.
Thank you.
Yeah.
So I guess adding on to Steve's question, there's there's like a literature on like handling survey data where you have to be careful about reading the responses of the surveys very carefully and then doing statistical adjustments because they're not exactly classified correctly. So I was wondering if there's like an analogous thing where if I use a transformer to classify something, when I compute regressions or statistical estimates on that data, I have to make some adjustments.
Yeah. So after lunch, I'm going to talk entirely about that. And so that's absolutely the right question. And I'm going to argue that you need to do that. And so, I'm going to spend the entire time after lunch or however much time we have to devote to that part arguing that that is super important. And we do actually cite that literature, like some of the seminal work by Angus Deaton in that literature. I mean, it's still, it absolutely applies to neural networks. All right. And so kind of the third type of problem you might want to do is you might want to make predictions about individual terms in your text. And so one classic example of this is called named entity recognition. So let's say we want to recognize every person that is mentioned in the text. And so if the token refers to a person's name, we want to tag this person and like specifically begin person and the inner person. And so we want to tag that, and then everything else would be other, right? Or we might want to tag locations, organizations, firms, kind of whatever kind of whatever you can dream up, universities. The list goes on and on. I want to tag in a biography who's the mother and who's the father. Anyways, the point is I want to tag things. I want to tag individual terms based on what information they contain. So that's called a named entity recognition problem. And there you just put separate classifier heads on each of the token vectors that come out of the transformer. And so that's in panel C. Or I might want to recognize spans of text. There's a question and a paragraph, and I want to say where's the answer to this question in that paragraph. And then again, you're gonna do classifications on the individual tokens. And so the general point of this is what's so powerful is before transformers, each of these problems would have a different architecture, like totally different way of solving them. But now, like transformers, you can just do anything. You get these vector representations and then you do whatever you want with them, whether it's classifying the text or similarities between text on the class token, whether it's classifying individual terms, and that makes transformers incredibly powerful. And I know I haven't talked about what transformers is like, so I'm just gonna leave this as a black box, but there's really amazing tutorials out there explaining transformers and how they work. So if you all aren't familiar, there's links to that in the knowledge base. And there's just videos that do a phenomenal job of explaining it. All right, so classification kind of in the sense that we've been talking about where you add a classifier layer, that's a supervised task, and so the model must see a sufficient number of examples from each class during training in order to perform well on unlabeled data. So if you want to classify, is this newspaper article about geopolitical risk, yes or no, you have to give it enough yeses and enough nos in training that it learns to recognize that. An alternative approach is that you can use generative AI for classification, and so you have a prompt and you explain to GPT, I would like to classify whether or not this article is about geopolitical risk. My definition of geopolitical risk is, this, yes or no. GPT, other models, they have structured outputs, so you can actually force it also to return, a yes or no answer. So in a JL article that I have on deep learning for 19 different topic classification tasks, all using historical newspaper articles from the US, we compared GPT to our own custom trained model. And I think the bottom line is that the custom trained models are almost always more accurate, but like sometimes GPT is really good. And you can just use that. So people ask all the time, can I use it or not? And my answer is always, why don't you just try it? Because it's cheap and easy to try it. So yeah, and in this case, we're comparing 3.5 to I think to 4.0. Or maybe 4 Turbo, and the time that it took to write this article and get it published, OpenAI made a lot of updates to GPT. Like there was a big improvement between 3.5 and 4. After that, not so much. I haven't tried 5 yet on these topics, but I will do that. But I have to say, kind of, we're still classifying things and using it. And I think the bottom line is like sometimes it works great and sometimes it doesn't, and it's always a little hard to predict, right? So Sendel and Ashish and others have an entire kind of fantastic research agenda on how AI is very non-human in the mistakes it makes. And so sometimes it can do a hard task, but it can't do an easy task. And they've done kind of experiments where they show humans are really bad at predicting what it's good at and what it's bad at, because it's not a human, doesn't behave like we do. And so, I always say like, just try it out. But you can see here kind of the pattern that emerges. And I'll also say that GPT trained means we took a Roberta model, which is an open source large language model, and we just trained it on the GPT labels. And the bottom line there is if GPT is not very good, that does terrible because the model's learning from bad data. But if GPT is doing really well, then that also does really well. And the reason why that's relevant is say you have 50 million things that you want to classify. You're not going to be able to afford to do that with GPT or Gemini or whatever your preferred model is, right? You're going to have to do it yourself. And but if GPT can do the task perfectly, you can use the GPT labels to train. And so I think kind of the bottom line here is like on things that are like really straightforward. Like, is this article about antitrust? Like GPT understands what antitrust is, and it does like really well. But there's other things where it just does much more poorly. Even like, say something like crime. I guess crime's just like a pretty diverse category. It doesn't exactly understand what we mean, even when we play a lot with the prompt. I guess I should say another thing here that's extremely important is you want to know how well GPT is doing. And so when you engineer your prompt, do that on a separate set of data from your test set. Because if you're engineering your prompt on your test set, you're just overfitting the prompt to your test set, and we have no idea how it does on unlabeled data. And so, there's a lot of things to go through here. Polio vaccine, that's really obvious, so it does really well. But some things, is this a schedule? Is this about sports? Those are all really like pretty straightforward. Horoscopes is very straightforward. Obituaries, but there's some things like, I think it's interesting, like it does way better on the Vietnam War than on World War I. And I think there's 2 reasons for that. Like there's just more about the Vietnam War on the internet and its training corpus, and so it just understands that better. And the English language has not changed so much in the past 100 years compared to some other languages, but it's changed a little bit, and sometimes that can just like throw a large language model for a loop, even though it's pretty clear to a human. So it does actually pretty poorly on World War I, articles about World War I, but much better when it comes to Vietnam.
Have you tried to see what happens if you take an open weights frontier model and you train it even lightly on these categories? Because supposedly we take an open weights model and you do some training yourself on predicting these categories. Would do really well because it gets rid of some of the simple mistakes from
that's essentially what I'm doing in the like columns 4 and 5. And so Distill Roberta is an open model with about 80 million parameters, and Roberta Large is like I think 320 million. And so I'm training those on on labels essentially. I think the bottom line is it tends to like almost always do better, but sometimes that better is very marginal if GPT is pretty good. We also tried Claude. We had a big problem with Claude. So Claude has this like constitutional AI framework, and they're really into AI safety. And so it kept on telling me that I was feeding it toxic content, and it refused to do it. And like sometimes you could understand why, but sometimes I didn't even understand why. It was just like an article, it's about World War I, and I guess it's kind of talking about violence, but nothing you would see as offensive. But anyways, like, yeah, we've never had GPT refuse to do something for us, whereas we had a lot of problems with Claude saying that whatever we feed it is toxic. Sometimes I did feel like I need to explain to GPT, I'm a researcher studying historical people. Don't want to get thrown off the platform for feeding it like, you know, op-eds from Hitler or something, which did exist. All right. And so again, I said the bottom line is try it. The other thing that can maybe be a downside is that models get deprecated and disappear all the time. You know, so you might hear on the news where people are really sad because they have like companionship with 4.0 and then it disappears. I guess the equivalent of that for us as researchers is like, uh-oh, I can't reproduce my findings. And so that's why like, it's always an alternative. Let's say you wanna classify whether something's an obituary, and GPT can do that perfectly, but you can also just have GPT do that perfectly for like 1,000 examples, train your own classifier, which will also be perfect. And then you always have that model, and so you don't have to deal with a data editor being like, what's going on? Like, why can't you be able to reproduce your findings? And so that's, you know, it takes, it's training a classifier is the task that I always have my undergrad arrays start with. So it's not completely trivial, but it's like about as straightforward as things can be. And so like, you know, if you don't want to take the risk of like people complaining that you can't reproduce your results because you did them with 4.0 and now 4.0 is gone, you know, there's always the option, you know, at least for things that are relatively like straightforward classification. I mean, I know with this article, it was in the JL, so it was the AA data editor, and they're like, yeah, like, we're okay with you using an, you know, OpenAI model. Obviously, it was the point of this table was to use it, but they're like, we're okay with that, like, even if it can't be reproduced, as long as you specify exactly what you did. So I think that's kind of in flux, like how we feel as a profession about the fact that these models are constantly disappearing. But that is one caveat to keep in mind. All right, so that is classification. And hopefully, you know, that's all pretty straightforward. And again, there's more kind of technical details. There's notebooks that you can use to train your own classifier, like on the Econ DL website. I don't think I've referred to that yet in the slides, but I will in a little bit. All right, so now I want to move to talking about embedding models. And again, I'm not going to go into the technical details, but I'm going to give you lots of examples. I'm going to talk about 3 different cases where it makes sense to use these. The first case, you don't know what the classes in your data are. You essentially want to explore your data. You want to make sense of your data by dividing it into different groups or different classes, but you don't know ex ante what they are. The second type of application is that you have a lot of classes, and it's just computationally unwieldy to train a classifier. And then the third type of problem is you want to add classes at inference time. So when we say inference in machine learning, inference is running your model. Okay, again, it doesn't mean the same thing as inference in statistics, so I know it gets confusing. So when we say we want to add something at inference time, it means you've already trained your model, and then you want to add new classes when you run the model. And you can't do that with a classifier because the model hasn't learned the weights to map into that class. But you can do that with embeddings, and there's lots of cases like, you know, where we would like want to do this. You know, so one example, let's say you're working with historical banking data, you know, and you have your own customized OCR, and then you realize like, oh, there's this little telephone symbol and it splits this, and I need that, or the OCR doesn't make sense. Well, there's not like a telephone symbol in your OCR. You don't want to go back and retrain the model. With an embedding model, you can just add it at inference time. And so we'll talk a little bit more about that as well. All right. And so, again, just to refresh, embeddings are the dense vectors produced by a deep neural network. And so if you have a text, there's gonna be an embedding for each token in the text. You can think of tokens as like words, although sometimes they're subwords if the word isn't in the dictionary, but think about it like words. For your text, you have this continuous vector for each word in your text, as well as an overall vector that represents the full text. Or if you're working with a vision transformer for each patch, which is kind of like an adjacent group of pixels in the image, again, you have a continuous vector representation of that patch of the image. And so we're gonna be talking now about working directly with those vectors. The first thing that I'll say is you generally do not want to work with the embeddings of off-the-shelf transformer models. So that would be like BERT, Roberta, GPT is just off-the-shelf transformer models. And the reason for that is they have some undesirable geometric properties. They're anisotropic. I don't want to go into the technical details of that, but essentially the space created by, say, a BERT transformer is not a convex space, and so it's going to be problematic when you start working with those vectors, because essentially the model hasn't been trained to work with the vectors, and there's holes in the space and whatnot. And so there's a big literature on this. But the key thing to know is that there's a method called contrastive training that can be used to make the distances between the embeddings and the vector space that's created by your neural network meaningful for your problem. All right, so the basic idea of contrastive learning is that you're learning a mapping from your unstructured data, so your text or images, to a continuous vector space, just like you would with any transformer model. But now you're training the model such that instances that belong to the same class have similar embeddings, and instances that belong to different classes have dissimilar embeddings. And so it doesn't have to be like a discrete class problem. You could train it on a continuous distance, but oftentimes we don't have that. So oftentimes what we're doing with contrastive learning is, okay, we're training the model to say, okay, if these two vectors refer to the same person, put them close together. If they refer to different people, so like say it's two different John Kennedys, not the same John Kennedy, put these vectors further apart, put them above a threshold distance. I'm going to show lots of examples of models that were contrastively trained. And that makes these kind of distances between the vectors meaningful for grouping data into groups of like things. And so all the technical details about contrastive learning are in this knowledge base. All right, the first thing I want to say is you might wonder, can I just use embeddings off the shelf, or do I have to tune it myself? Because from OpenAI, for instance, you can go and buy embeddings, and they're actually very cheap. And so OpenAI will sell you, I don't think they sell you for the individual terms, but they'll sell you the embedding for your full kind of text that you put in. And so you might say, well, can I just use the off-the-shelf ones? And I think in this case, the answer is kind of almost always no, because your vector representation of your text, that contains a lot of information in it, information about the syntax, the semantics, the topics, but maybe all you care about is the topics, right? And you want to tell the model that by giving it some training data where you make those vectors closer if it's on the same topic and further if it's on different topics. And if you don't do that, the model doesn't know that you're interested in the topics. Maybe it more pulls out like, okay, these two have similar syntax, but that's not what you're interested in, right? And so I want to give an example of this that comes from the comparative agendas data set. This is a data set, you can go download it online, which is why we used it for this example, and it has really high quality topic tags about legislative acts. So think about this as bills in Congress, acts of parliament, etc. And it divides them into different detailed classes. And so we can use off-the-shelf embeddings. So probably the most well-known off-the-shelf contrastively trained embedding model that's open source. It's called SentenceBERT, and we use SentenceBERT a ton in my research. It's open source, it's super easy to use and tune. They have it for many different languages. They have it trained on different things. It's a really useful resource. And so we look at the SentenceBERT off-the-shelf embeddings, meaning we haven't trained them at all. We look at OpenAI off-the-shelf embeddings. We just take them from OpenAI. We don't do anything with them. We just say, do these group-like topics together? And the answer is not very well. But if we train on a limited amount of data, so even just hundreds of pairs, going to thousands of pairs of data, it starts to do a much better job. And I want to show you that with some figures. So this is SentenceBERT embeddings off the shelves. And you see the cosine similarity, so a measure of how similar embeddings are within topics and across topics. And like with cosine similarity, the smaller it is, the more similar they are. It's like, the angle between these two vectors. And so you can see in blue that embeddings in the same topic, they are more similar than embeddings across topic, but there's a lot of overlap in that distribution. So you're gonna have a hard time taking these embeddings, clustering them, and pulling out coherent topics because there's just too much overlap. And that's because these embeddings also think about, the syntax and everything else that's in the text and not just the topic. And it looks basically exactly the same with OpenAI. It doesn't really matter if you use a larger model, it still doesn't understand that what you care about is a topic. But here we fine-tuned, and you can see you get much better separation. It's still not perfect, and basically if you look at this overlap, it's because this data set assigns every bill, every act of Congress one topic, but some of them are multi-topic, and so most of the cases of overlap are genuine, this is actually about two topics and the label's not perfect. So it does much better. We can take this model trained on US bills, take it to Acts of Parliament in the UK, and it still does reasonably well. And so there's some amount of transfer learning that's possible there. But the bottom line of this is just, you might need to tune your own data. Fortunately, one of the really powerful things about contrastive learning is that it's extremely sample efficient. And so sample efficient means you don't need to see a lot of training examples compared to some other much more complicated architectures, much more complicated models that are out there. And so if this is kind of abstract, what I want to do now is to give you a bunch of different examples of how we've used embedding models, contrastively trained embedding models, to measure things and perform tasks that are of relevance to economists. Okay, so the first thing I want to talk about is detecting reproduced content. And so in this case, we have some noisy data. It could be data from the internet, so C4, which is the cleaned corpus of the internet that essentially is what large language models are trained in large part on. It could be historical newspaper articles. We've looked at both of these examples. And so I was, from a social science perspective, I'm really interested in historical newspaper articles. Historically in the US, about half of content in local newspapers came from a wire, a news wire. The most common one is the Associated Press. But the articles, they won't be exactly the same. Local papers abridge them, so it will fit on the page. There's also OCR errors, and actually there were kind of different versions that came from the Associated Press. We call this choose your own adventure because they put the controversial things at the end of the article and then say, may insert after line 2, may insert after line 7, and you could choose, what politics I think the article conveyed by choosing to insert those things. And so they're not exactly the same, but they're pretty similar. And so that's one application. I also have some work with other computer scientists where basically what we found is OpenAI did not adequately deduplicate their training data with the test data, with the benchmarks that it's evaluated on. And when you look at how GPT-3 performed, it did much better on benchmarks that they did not get out of their training data because they were just using 13-gram overlap. If there was a 13-gram overlap, they took it out, but the internet's noisy, there's lots of small differences in punctuation or whatnot. And so this issue really, noisy duplicates really influences how we interpret how well large language models do, because if you don't deduplicate, the test data out of your training data, then it's like cheating essentially. But I'll talk about reproduced content since that's maybe more interesting to us as economists. And so we developed novel methods where essentially we trained a model on labeled data to say, does this article come from the same newswire source or a different source? So we contrastively train that, starting with an SBIRT-based model, and then we cluster. And we use single linkage clustering because that's incredibly scalable. Things like hierarchical agglomerative clustering won't scale the large problems, but single linkage will. We do community detection, which helps to break some of the false links from single linkage since it's kind of the most scalable, but not always the most accurate method. And so we do that, we embed a massive number of newspaper articles, and then if it's in the same cluster, then we say it comes from the same newswire source. So this is very accurate. This is reporting here the adjusted RAND index, which ranges between 0 and 100. It's probably the most commonly used measure of clustering, like how well is your clustering doing. When we compare it to the non-neural method, so just looking for, n-grams, common n-grams, or hashing, which is a computationally efficient way of looking for common n-gram overlap, it does much better to use this neural method, because small differences can break looking for exact term overlap, but the neural network can account for that, and I won't make the distinction between the first and second lines. Essentially, we just have like an extra step that can increase accuracy, but also makes it less scalable. And so I want to talk about, well, what did we do with this model? We released a data set called a Newswire data set, and we start with about 138 million front page articles from historical local US newspapers spanning a 100-year period. And we find, kind of using this model, that there is about 99 unique articles, including singletons. About 2.8 million of those are reproduced more than 4 times, or more than 3 times. And then we kind of reduce to wire articles, get rid of syndicated content. This data set is all available on Hugging Face. And so if you're interested in these historical newswire articles, you can go and just download this data set and use it. There are OCR errors. We're slowly cleaning this on GPT, but we just use the 10 million free tokens we get a day. 10 million tokens might sound like a lot, but we calculated it would take like 180 years or something to clean all unique 99.4 million. But if you want to use it, a subset of it, you can also clean it. We include other information, so we extract, again with deep learning, we extract the dateline, which is where the article was published. You see articles coming from across the US. This is international datelines. I mean, you can clearly see wars in this figure, so it makes sense. We have topic classification models, and I think that this is pretty interesting, like say on crime, you can see the prohibition spike, on protests, you see the 1960s. These are high quality kind of topic classifiers that we trained ourselves with our own labeled data. We also use topic tags from the comparative agendas, which are maybe not quite as high quality, but kind of give us more topics, and those are available as well. All right, another thing that we did related is, so local newspapers, they got their articles from The Wire, but The Wire didn't give headlines. Their editors wrote their own headlines. And this is pretty cool because it gives us a human-made data set that's different ways kind of to say the same thing. So we released all these kind of pairs of headlines that appear here, and so you can see that there's just kind of a massive number of paired headline data that are kind of 2 headlines for the same article saying different things. This is really interesting from an ML perspective because it's great for training semantic similarity models, but also from a social science perspective. I mean, sometimes it's, they just wrote a different headline, but sometimes you can clearly see the politics and kind of the different interpretations of the same thing in it, which is pretty interesting. Again, it's all on Hugging Face. All right. The final thing I want to say is that this model is incredibly computationally efficient. So this is for a paper we did. We looked at deduplicating 10 million articles. Most of the time is to embed it. This is just on a single GPU card. But we can do the 10 to the 14th vector calculations in about 3 hours on a single card. So once you're in a world where your data is in dense vectors, it's just, you can do things at an insane, like unbelievably insane scale, very cheaply. It's not a fancy GPU card or anything. We bought it in 2020. There's 4 cards on the machine. It wasn't that expensive. And so this is a card that like my students can get with their very limited research budgets. All right.
So have you also thought about using the sort of GPT as a kind of sort of creative tool to design research questions, or in some sense, so now you've got these newspapers that have been digitized in the archive, you can start to imagine what statistics locally are reflected, how should I classify these data in order to capture some local variation that's not captured in official statistics. So kind of sort of a higher order reasoning or sort of use the model itself to guide the research question. Does that make sense, or is that meaningless, or you think this is the scope to do that?
I mean, I think part of the challenge would be like the scale of the problem, so we have like in total like over 1 billion articles, like, and yeah, we can deduplicate them and then that like cuts down, but there's just like so much content, like, and it's not like you could put all that content into a prompt. And yeah, I mean, so I think it's like, I think it's an interesting idea, but you'll see kind of other ways that we've tried to make sense of what is in this data, which is what my other examples are going to show you too. But like none of this uses GPT because I think you kind of need it to be customized, and the scale would just be like completely infeasible. Like even using many, which is the cheapest, it would just be very, very expensive. Whereas with a much lighter custom trained model on our own machine, we can run it really easily. But obviously there's things you can't do. But going exactly to that point, one thing we wanted to say, okay, is what was the biggest news story of the year? We have no idea, like ex ante. So we can't build a classifier. And so what we did instead was to take data from this website, All Sides, and for modern news articles, it will collect, like, say, here's these 5 different articles about the same story. One's from Fox, one's from the New York Times, one's from CNN. So we use that to train a customized model, starting with the wire cluster model as the base and then tuning it to put things that are about the same story from this all sides data close together and things that are about different stories further apart. And then we cluster the resulting embeddings. And we did this on the American Stories data set. This is 20 million newspaper scans that we digitized from Chronicling America collection. And so we apply it to these data. And these are the biggest stories for each year. I think it's pretty interesting as an economist that a lot of these stories are about economics and specifically about labor issues. Like you see lots of stuff in here about strikes. Obviously, you also see a lot of stuff about conflicts. And then there's really random stuff. 1909, race to the North Pole. So there were these 2 guys who were racing to get to the North Pole first, and they had a big fight who got there first. And like it was just like coverage of this fight for an extended period. I guess not much else was happening in 1909. So sometimes you get random things, but mostly it's pretty interesting, and economic issues like certainly mattered. So for labor historians, there's a lot of material. Okay, a final version of this, which was just essentially like for fun, is we took that model, we mask out named entities, which are essentially like proper nouns, like locations, organizations, individuals. And then we say, okay, for a modern news article, what's the closest historical article? You see an example here. Mostly this just provided us with entertainment. Again, the model is like online. I'd like to build out like a better version of this where you can put your own article in, but that takes money that I just don't have lying around at the time. But It's really fun to play with. I mean, maybe it's interesting to people here, like we pulled out various articles and I'm convinced like people in the 50s thought that like AI as we have it now would like exist by 1965 or something like that. Like they really did. So it's interesting for thinking about, optimism in tech. We had a lot of fun with like campus protests and like university issues because it all goes to the 1960s and like you see the same things like, if you don't like, get these protesters off the Berkeley campus, like we're defunding Berkeley and like suspending all like federal research funding, but they didn't actually do it. Nixon didn't do it, but he had the idea. All right, and then I'll finally say you can do the same thing with images. And so this is just the same idea where we have, and here this is mostly trained on synthetic data because you can synthetically like crop and noise images. And we can figure out what's the most reproduced newspaper images in a given year. Again, you have this custom trained model, you map all the images to vectors, and then you just cluster. So not surprisingly, like the most reproduced image of 1969 was the moon landing. Just a sanity check, most reproduced one of 1967. I'm just showing you some fun examples here. I guess it doesn't really have a point, but people love showing like violence in progress. This is a case where this guy was standing trial and he smuggles in a gun and takes the courtroom hostage, and they got a picture of it. So that was the most reproduced image of 1970. Obsessed with plane crashes. People ask about women in the press, and so almost all the pictures are of men. I had a student who was labeling images for this, and she's like, I've been labeling all day. There's only one woman, and it had her waist size in the caption. It was like probably homecoming queens are the most common thing, but we did find these popular images. Jackie Kennedy, of course, the Manson murders. There were these like nice looking women who were in a cult and murdered people, but not a lot of women. This is just in case you fell asleep during the other stuff. Maybe this is entertaining. I mean, a more serious thing that we wanted to look at is there's all these news articles about images that change history. People talk a lot about the napalm girl image. Okay, so I'm going to show that image. Hopefully it's not too disturbing to anybody. This is an image of children in Vietnam being burned by napalm. There's another famous one of this Viet Cong soldier who's about to be executed. And there's a lot of people who say this changed history. This made Americans realize that, that we should get out of Vietnam. And so we're like, well, is that true? We found that the image was not very widely reproduced. It did run below the fold in the New York Times, but people didn't like the frontal nudity. We find no impact on abnormal stock returns of Vietnam War contractors. There's a minimal but very small and short-lived abnormal return of Dow Chemicals who made napalm. If you look at mentions of the napalm girl photo, they take off only after the woman who's in it started a public charity in the 1990s. So I think this is pretty interesting. It's kind of, and you see this mentioned a lot, today when something relevant comes up, the drowned, Syrian refugee toddler, and Angela Merkel mentions that, and then people start talking about Napalm Girl and how images can change things, and it's more like we filter the past through the present, and when you can go and actually see the past as they saw it at the time through newspapers, it can look very different than how we remember it. All right, so I want to shift gears. Like all the examples I've showed you so far are about cases where we kind of essentially want to explore the data. We don't know what's in there. Another reason we might want to use embeddings is because we have a lot of classes. So let's say you want to merge the 1930 and the 1940 US Census. And there's millions of individuals. You want to, merge firm databases. You have a lot of different classes in them. So record linkage is fundamental. Anytime you might need to link, individuals, firms, products, relatedly, you might need to aggregate, products into industries, et cetera. These are very, very common kind of data challenges that we face before we can do the analysis that we care about. And it turns out that deep learning is really powerful for them. And so traditionally, we link records with string similarity. The problem is string similarity doesn't understand semantic similarity, co-incorporation, they mean the same thing, we know that, but they're very different strings. So what I did is work with a student, Abhishek Arora, to build a package called Link Transformer that aims to make it easy to use large language models for tasks like merging, deduplication, clustering. And so it supports standard merging, merging with blocking or multiple keys. One thing that I think is kind of fun is you can bypass translation by using a multilingual large language model to link across different languages, which is a domain where, you know, traditional record linkage with strings is terrible. You can use it for aggregation, so say aggregating products into industries. We also allow you to train your own classifier with it. And it supports any model in the Hugging Face Hub, or you can just directly use OpenAI embeddings. And we have our own models that we train for 6 different languages for different types of tasks. So mostly like linking firms, linking products, aggregating products into industries. You can go see the paper and see how well it does, but just the punchline is it does way better than string matching. And usually your customized thing does better than using OpenAI embeddings, but OpenAI embeddings can be decent if you're doing something pretty simple, and they're very easy to use. And so the idea here is, let's say we have a bunch of firm names, we have some link transformer model, we use that to map those firm names into vectors, and then once we have vectors, we can compute distances between them, and that's a distance, just like edit distance is a distance, and you can use these vectors in the same way you'd use edit distance, but unlike string distance, these distances account for semantic similarity. We try to design the package and so that it's familiar to people coming from environments like R or Stata. Like this is in Python, you would not be able to do this in R, but we try to make it intuitive. We try to make it intuitive to train your own model. So the basic functionality is, we have lists of firms and we want to merge them together. You do that with a simple line of code. As I said, really, I have like abandoned projects because I'm like, I cannot link products across 2 languages unless I do it all by hand. But now multilingual language models make that easy. Here's deduplication, again, kind of same principle. Aggregating products to industries. I mean, there's always some ambiguity in which products go into which industries, but we use like data from the UN on product classifications, and we evaluated this on historical data, before you had those UN classifications, and it does pretty well. One of our motivations was studying the impacts of import substitution industrialization. We have these tariff schedules, and every month they change the name of the products, and you need to be able to link them together, and this was before harmonized data, so there are no codes. You just have the description of the product, its name, and the tariff, and we were able to get really high accuracy using this model for those products. It's pretty straightforward to train a model. Okay, so that's using large language models for record linkage. I'm probably overwhelming you with examples, but I want to say you can also use vision for record linkage. This would probably be unnecessary if you're working, say, in a Western language, but it's super useful. I think when working with, say, traditional Chinese, Japanese, character-based languages, because OCR is still not as good, the vast majority of the time as we wish it were. And you can account for the fact that you can account for the visual similarity between characters. So again, I work with a group of students. We contrastively trained a model on digital fonts to measure character similarity. So basically we used a bunch of digital fonts and taught the model, characters, the same character in different fonts, give those similar vector representations. But it turns out that this actually works pretty well across fonts. And so you can see here an example character, and then you look at the most similar character, and we've done this for different Asian languages. And you can see it kind of tells us pretty well which characters are visually similar. And then that allows us a very cheap way to do kind of better merging that accounts not just, are these the same character or not, but it accounts for the similarity. And because oftentimes, let's say names in Japanese, they're like 3 characters long. If you get one of those characters wrong, you are not merging your person. Like you just lost too much information. But when you take into account the visual similarity and the types of errors that are likely to be made in digitization, it makes it much better. We had fun applying this to ancient Chinese from, I think like 1300 BC. And so these are ancient characters, what the ancient character meant and the modern character that descended from them. And it's just really interesting because the characters that the model said were visually similar, like archaeologists say that these have similar abstract meanings. So kind of these ancient people, when they drew a picture for like more abstract things, like things that had kind of similar meanings, they drew more similar pictures. So again, I'm not sure this has any economic application, but it was easy for us to do this and it was fun. All right, the final thing you can do is say, I want to use both the language model and vision. And so we did this in a paper called Clippings. It's a multimodal model. I don't want to go into the details of how we did this because it's pretty technical. And I think like working with a model like this does get pretty technical. When you're working with kind of multiple modalities, it becomes more involved. But basically, we were trying to link Japanese firms across time, and we wanted to use both the visual appearance of the characters, but one of the documents was written horizontally and one was written vertically, so that we could account for problems with the OCR and very similar characters. But we also wanted to use the semantics because you write firm names differently, but they mean the same thing. And so when we took them both into account, we got almost perfect merging, whereas using just language or just vision was like, okay, but like not as good. One of the things that we were interested in this Japanese data for was to look at antitrust policy that the US implemented in Japan after World War II. They came in, they tried to break up a lot of large Japanese firms, but the Japanese had various ways to get around this. And so when you look at input-output networks in 1957, which is a few years after the US left, and you look at the big firms that they tried to break up, which are the kind of colored dots there, they're still the most central firms in Japanese input-output networks. And so basically, we would have never been able to kind of link firms together in the multiple sources we needed to put together kind of full input-output linkages if we hadn't been able to use deep learning for record linkage. I think it would have been hopeless. All right, I want to give one more example of record linkage, and I think this is really cool. And so I've been talking so far about kind of traditional, merging. We have 2 data sets that firms appear in or individuals, and we need to merge them. But another kind of merging task is with unstructured text. And so we have these historical newspapers. I was asked before, how do you explore what's in them? There's billions of mentions of people in particular, and we'd like to understand who is the newspaper talking about. And so what we'd like to do is we've already done named entity recognition to tag all the individuals, and then we want to say, does this individual appear in Wikipedia? And if so, who are they? And so what we do is to contrastively train a model, and we did this on the Wikipedia disambiguation pages, which are pages that list, say, all the John Kennedys that appear in Wikipedia. And so that gave us literally billions of pairs of training data for free. So we didn't have to label our own data. We could get that from Wikipedia. And then we embed the mention of the person in the newspaper article. We embed all the first paragraphs about Wikipedia, and we tune it a little bit on some labeled data so that the model, if it's President John Kennedy, it puts it close to the John Kennedy page. If it's local councilman John Kennedy, it's far away from everything in Wikipedia, and we say, this person is not in Wikipedia. And I think this is impressive because there's millions of people in Wikipedia. There's even more people in our newspapers. Just a sanity check, who are the most mentioned people? Label is pretty much what you would expect, Hitler, Eisenhower, Nixon. I think it gets interesting when you think about who was mentioned historically but is not in Wikipedia. And so the most commonly mentioned person historically in our newspapers, not on it doesn't have their own Wikipedia page, was the guy who was manning the phone lines at Pearl Harbor when Pearl Harbor got bombed. And so basically he gets called, and the guys with the scopes looking are frantically being like, the Japanese are coming, you gotta move the fleet, like, and this guy was manning the phone, so he told his boss, and his boss was just like, whatever, like, and he just didn't care, ignored him, I'm doing something else right now. And they're just calling him frantically, and the guy thinks about, should I go over my commanding officer and tell someone else, but in the end he doesn't, and then Pearl Harbor gets bombed. But I guess we don't like to remember that. Like, I never knew that. Like, Pearl Harbor got bombed because the Americans were really incompetent versus like the Japanese were this amazing force who we then defeated. It's not like, it goes back to how we tell history. Versus what actually happened. But anyways, you can imagine a lot of different applications of being able to do something like this, because once you get to Wikipedia, you have Wikidata, there's tons of structured information there, and then you can kind of, there's a lot that you can do. And so this was essentially, again, this is using embeddings, a vector representation of the mention of that person in the article and the context around them, a vector representation of the Wikipedia text, and with that, you can figure out with like reasonable accuracy, and you can go see the paper, who's who. There's other methods, and we compared all of those in the paper. An advantage of this method, again, when you're working with these vector representations, it's just insanely computationally efficient. And so, as social scientists, it doesn't matter, like, we're never gonna have that great of a compute budget compared to like OpenAI or whatever. So we have to think about computational efficiency. All right, a final application, adding classes at inference time. And I'm gonna talk about this in the context of OCR. There were other reasons we wanted to design our own customized OCR architecture. The traditional architecture used by OCR is a joint vision and language model, and it's very sample inefficient to train. And so, we had these Japanese documents. The best OCR available anywhere was Baidu, and it got like over half of the characters wrong, which is not gonna cut it. We needed to design our own customized OCR, but we would never have enough training data to tune this complicated language vision model. And so what we did was essentially to treat OCR as an embedding problem. I'm showing this here in Japanese, but we also did this for English, and our newspapers are digitized with our model for English. And so we recognize kind of individual characters or words, right? In an Asian language, characters are words. And we embed those with a vision model. And then we just compute the nearest character in a digital font that we've also embedded with the same model. And that's how it's transcribed. And this compares to the bottom row, which is traditional OCR architecture. It's an architecture called sequence to sequence. You're not recognizing individual words or characters. You're dividing it into patches, and then it's very complicated because you have a vision model and a language model, and you have to jointly tune those, and that's really computationally efficient. Just using vision, it works really well. It's super sample efficient, and so those top two lines on the left are an open source transformer model that Microsoft trained on 670 million images. And you see it just does nothing. It doesn't get any more accurate when we train that architecture on our data, whereas ours, which is the orange, it learns very efficiently. Again, if you're digitizing English typewritten stuff, just use GPT, okay? It's amazing, actually, and it can, like, pull out stuff, and it's great. I think it's really transformed a lot of stuff that I have to OCR, but if anybody here is working with, weird stuff, old handwriting, Asian languages, we have this custom OCR package. We try to make it super friendly. There's a notebook, and you can, train your own OCR for ancient Greek that works really well and beats Google Cloud Vision with the notebook. So yeah, that's my bottom line on OCR is if you have to do standard stuff, you're very fortunate that you're doing it today, because GPT has made things so much better. Just really in the past 6 months, it's gone really good. But that's like typed English or maybe neat handwriting, But if you're doing stuff that's more off the beaten path, this will be useful. Okay, I have just a very quick word about regression. So again, in machine learning, the term regression refers to the prediction of continuous numbers, continuous outcomes. And it basically works just like classification. You add a layer to your neural network, but now that layer is predicting a continuous number instead of predicting the class scores. And one example of this that comes up in economics a lot is document image analysis, where we have some documents and we want to get structured output. Traditionally, there were no good ways to do this. You'd have to bring together, lots of different tools from different sources and be pretty technically advanced. Back, like 5 years ago now, I worked with a couple of pre-docs, Zheng Shen and Jake Carlson, to design an open source package called Layout Parser for document image analysis. And it tries to make it really user-friendly. This is an example from the paper. Obviously, it's an easy example, but it's, with a single line of code, it's detecting the layouts on this page. This is an example of something we did, that's a bit more complicated. We want to customize it to detect headlines, captions, etc. of newspapers. If you send this to Google Cloud Vision, this is what it does. It reads it like a single column book. It's a problem with the OCR output too on sites like newspaper.com. It gets scrambled up oftentimes because the layouts weren't properly detected. But with our link transformer package, we can pretty easily detect layouts. I will say that the thing about layout detection is there's no foundation model for doing this. You're just starting with something trained on ImageNet, which is images of dogs and cats and things like that. And so you pretty much always need to tune your own model. If GPT can't figure out your layouts, which oftentimes it doesn't, and you need to figure them out. We have base models on Layout Parser, but you do oftentimes need to train your own data, but you can do that often with hundreds of labels. It's not super costly in terms of labeling data. This is another example. This is the Japanese firm data that I was talking about. Used to look at antitrust policy, so we divide into columns. We use deep learning to recognize the different pieces of information. All right, so that was a very quick overview of regression. Basically, if you understand classification, you understand regression. And so in short, deep learning provides really powerful tools for processing unstructured data. I found it very, very time intensive to learn all this stuff because there was no resource. I was very grateful, one of the first classes on neural networks on kind of even pre-transformer was at Stanford in 2016. Those lectures are still online. I learned a lot from that, but basically I had to go to the internet and learn a lot of stuff myself, read papers. And so I put this all into a knowledge base, linked a lot of resources. I hope that makes it easier for people to get familiar with these tools. Of course, you might say, well, these models aren't perfect. How do we need to account for that in research, which is what we will talk about after lunch.